Right, welcome back. We're back out here and we're going to cover, only two more topics, okay? The first one is acoustics. I talked a little bit, right, in properties of sound. We're talking about sound waves. What is sound? What are the objective properties? What are the subjective properties? Okay, now sound waves. As you can see, is a little loudspeaker traveling to our ears. Now, those blue dots that you see in the middle, blue or green, right? Blue dots you see in the middle, those are actually the air molecules. So you can see the ones that's thicker, the darker bands of air molecules, that's where the air is being pressurized. Then you can see the ones where the air molecules are a little bit further apart, that's where the air molecule is being rarefied. So you have compression, you have rarefaction. So compression, the pressure is high. Rarefaction, the pressure is low. And the analog of that, right, is in the sine wave that you see, right? This waveform. So sound waves exist as pressure variations in a medium, for example, air. Sound waves, right? It's not really that the sound, some mysterious particle, right, is traveling from my mouth and then reaching your ear. I'm actually causing pressure variations in the air, right, between the sound source, my mouth, and your ears. Okay, so that's what's actually happening. Right? It's not there's a particle that travels here. Actually, there's no particle traveling. It's the sound waves that is traveling. So it's being created by vibrations which are transmitted through the air, reaching the eardrum, which is then interpreted by the brain as sound. A few topics covered earlier, right? Amplitude, the level or the intensity. So it refers to the difference between the maximum and minimum pressures within the sound wave. So I talked also about properties of sound, about frequency. So we have low frequency, right, where the waves are wide and far apart, and high frequency, right, they vibrate many more times per second. So frequency refers to the number of waves, the pressure, the peaks that occur in 1 second. So for example, right, on a bass guitar, 4-string bass guitar, the low E, right, gives you a frequency of 41.2 hertz, about 41 hertz. Then the middle C on the piano is about 261.63 hertz. Then wavelength. So wavelength is not a property of sound, it's one of the measurements of parameters. So wavelength is the distance between any point between one wave and the next wave. So it can be anything. So you measure it from the peak of one wave to the peak of the next wave, right? Or you can measure it from the 0 point, also can. Now this is dependent on the speed of sound. Anybody remembers what's the speed of sound in air? In meters per second. Forget already, so fast. Okay, go back and look at your notes again, right? Dependent on the speed of sound in the medium divided by the frequency of the wave, okay? All right, so maths formula again, okay? But this is actually very, very useful, and acoustics really, really relies on this. So wavelength, the Greek unit for it, we call it lambda. So wavelength equals to V, the speed of sound, V, velocity, divided by frequencies, right? So whereby lambda is the wavelength in meters, V is the speed of sound, and F is the frequency. So you can always determine how long the wavelength of a particular frequency is. As long as you know two of the values, you can find out the third one, right? Mathematic formula. Let's move on. What is interference and phase? Throughout the whole workshop, I mentioned phase many, many times, right? So we know what are the things that it does. So we know how it sounds like. We know that, if something's out of phase or there's phase cancellation, we know that it's generally bad. So what is all this? For example, right, wave interference occurs when the sound waves meet each other. It could also be, from two different sound sources, or maybe the other way around, okay? Right, two different microphone captures, right? It captures a different waveform. The interference depends on their phase relationship, right? Or phase coherency. You hear me that I use that word as well, coherency. So when something is in phase, the waves they are constructive, so they add together. Now, if it is 180 degrees out of phase, so if you go to, right, on any DAW, you have your phase polarity invert, or even on an analog mixer, right, you have the polarity phase. What it does is it flips it 180 degrees. So if you do 180 degree of the wave, you cancel each other out. And what you get is 0. you get nothing. If they perfectly cancel each other out, okay? So if you have different waveforms, if they add together, right, the sum result in the end is a entirely different waveform altogether, okay? Right, let's move quickly over the next one. Those are some of the basic things which related to sound waves, okay? The basic behavior. Let's go to the next one. Understanding acoustic treatment. Very important. First point, if you can't remember all those things, you cannot remember all the other details, remember this. Remember this. Acoustic treatment is not soundproofing. I think now if you go online, you go to Shopee, Lazada, you see all those things, right? You see soundproof foam, soundproof this, soundproof that. Okay, I can tell you immediately if they use those terms, right? They already, first of all, they don't know what product they're selling lah. So foam is not a soundproofing material at all. Maybe if you use foam that is 50 feet thick, maybe can lah. Okay, right? That's as thick as this whole wall. Maybe it'll help to soundproof lah. But the foam that you see here, right? 1 inch foam, right? Usually is 1 inch or 1.5 inch in thickness. It's not a soundproofing material at all. It is used for acoustic treatment. Let's say you have a typical room, right? A square room is the worst. Like a cube room is actually the worst lah. So a room with acoustic problems, right, will compromise the accuracy of your monitor speakers and your equipment. So if the room acoustic is not good, what you're hearing through the monitors is not accurate. So what you're trying to record, you're not capturing the actual accurate sound. Then when you try to mix, okay, you are not hearing the accurate representation of the speakers. Then when you listen, you mix ready, you take it back, you listen somewhere else, it's like, why is it off? Why is the bass off, the frequency, mid-range off? So it affects your accuracy. So room problems, right, can be divided into two main categories. Number one is the reflection, right? Reflections. So reflections here, we usually talk about the mid-range and high frequencies from the hard surfaces, right? For example, the walls, the ceilings, hard surfaces. The table that you're on, you have a desk, that also can be a reflection. Or if you're working on a large mixer, a large console, the surface of the console also gives you problems in relation to reflections. So number two, right, the second problem is peaks and also the dips down, right? Boosts and cuts in the low end response. So this is usually caused by the room dimensions, right? The size, the length, the width, the height of the room, and also some because of reflectivity because of some reflections as well. Room modes. What are room modes? Room modes are created when a room dimension coincides with a particular frequency's distance of travel, right? In this sense, maybe the wavelength lah. So what happens, let's say, it occurs when the room dimensions are the same as the wavelength. So let's take, for example, a wave that has a wavelength of, let's say, 10 meters. Right? Easy to calculate, all right? So 10 meters, let's do a wavelength. So 10 meters, where it's speed 230, right? Divide by F to get you 10 would be 33 hertz. Okay, right, very easy. So 10 is very easy. So if a frequency of 33 hertz, if I'm not mistaken, should be like about a C. Like if you have a 5-string bass, right, is maybe a C or C sharp lah. That note, okay, on a 5-string bass. So if you have a room dimension that is 10 meters long, it could be either the panjang, the length, the width, or the height. You're going to get a room mode. Right, there will be a room mode. It can also happen at half the wavelength. So it can also happen at 5 meters. So if you have a frequency that's at 5 meters, so you double that. So at 66 hertz, for example, you will have a room mode there as well. Then a quarter of the wavelength, 2.5 meters, it happens there, so on and so forth. So now some of these bass frequencies, they will cancel each other out. If there is a bass frequency, imagine inside this room bouncing each other due to the reflections that are out of phase. So if a frequency bounces from this room, then it bounces back there again. And then on the way, it meets some of the frequency. It meets the same frequency at the same intensity curve. It causes cancellation. Whereas at other frequencies, it becomes in phase, then it gets boosted. So very easy. All right. You go to any room, especially, right? You listen to music. Go back home. You turn on your spare speakers. Maybe choose something that has got really good bass. A song that's got nice deep bass. Okay. You walk around the room. The most obvious change you will hear, the difference is the bass, the low frequency response. You hear at some points, the low frequency goes bigger, louder. At some points, you will hear that the low frequency is reduced. right? And then if you go to a corner, that's where the bass frequencies will be boosted most of all. So this is what we call modal ringing, right? So that means, those room modes at those particular frequencies within the room, based on the wavelength, right, and the dimension, the size of the room, you get those boosts and cuts. Every room will have this problem on, like no matter how perfect, there's no such thing as a perfect room. So this is they call this a waterfall display, right? Basically, you can actually use this, right, as a measurement. So for example, let's look at, bottom there is all the frequencies. Top is all the level lah, right, in dB, and the front to back, okay, because this is a 3D display, is your time in milliseconds. So you can see, for example, if you have a take for example here, so at about, this is maybe about 180 hertz, you have this frequency that rings, right? That means after the sound supposed to die off, that note still rings. Okay, actually, if you pay attention, if you listen, every room also, hey, 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 there will be ha, ha. Okay, it's a bit hard to hear, right? I can't generate enough low frequencies. But if you have a bass guitar, sometimes you play certain notes, you play. Sometimes you hear certain notes will ring. Boom. I'm sure you've gone to some rooms, right, where you hear some ringing frequencies, right? Even if you talk, right? Even if you talk or there's some kind of sound source, that's what we call modal ringing. So it means that this frequency kind of rings out a little bit longer. Then you have room modes problems at that frequency lah. It's problematic because it means that every time you hear that frequency, right, in your mix or in your recording, that frequency is going to it sounds louder than it is. It gets boosted, boom. You get a bit of a boom there. So what happens when you hear the motor ringing? You feel like, alamak, oh, this frequency is booming lah. I cut. But what happens? Then when you listen outside in a car, you listen on headphones as well, it's like, why that frequency is missing? Because you cut it. Because it sound in your room, it sounded like that frequency was booming, you see. Right? But in reality, it's not. It's because of the modal ringing. So it's where the monitor speaker placement also important. So if you place it inside a room near a spot or a note where there's a peak, right, that excites, for example, 100 hertz. Every time you get the note 100 hertz, right, that's about a G sharp. When you get that note suddenly sounds louder. Okay, right, it will ring there. So, but then if you locate it near a dip, then the 100 hertz sounds softer. Then you always feel like, 100 hertz not enough lah. You always boost. You boost. Then same problem. You take the mix outside, you listen elsewhere, you listen to other speakers, it's like, wait, why so boomy there? Okay, it's caused by all these issues in the room. So likewise, if you're a listener, right, as I mentioned, you try and go back and do this experiment. Listen to some music. You go and listen around the room. You will hear some parts, the bass frequency will be louder, some parts it will be softer. So this leads to over or undercompensating for that frequency by boosting, cutting EQ, resulting in a mix that does not translate well. Let's continue. So there are 3 types of room modes, okay? This one is a bit theoretical, right? But just so that you know, there is the axial. Axial will be between 2 opposite room surfaces. For example, between these 2, right? And maybe the front and back, and the top and bottom, axial, okay? You have tangential, from the word tangent lah, okay? Tangential can be any 4 room surfaces. This one is a bit more complicated already. So if I have a frequency that bounces from here, then diagonally bounce there, bounce back. You can also get room modes in that way. Third one, oblique. All 6 room surfaces. Remember, every room actually has 6 surfaces, okay? Don't forget floor and ceiling, okay? This gets very complicated, all right? Because you can trace the lines, right? 6 different surfaces, they interact that way. Now, for acoustic treatment and for acoustics, right, we primarily only concern ourselves with the axial modes, okay? Because they are usually the ones that give the most problems. Oblique, because they bounce around so much, sometimes the energy gets dissipated, so it's not so much of an issue. So axial modes, because they're the ones that give the most effect. Next thing, another problem is Flutter Echo. So Flutter Echo, right, you probably have heard it. It's caused by a distinctive ringing sound caused by echoes bouncing back and forth between hard parallel surfaces. Now, I've not actually gone around. Any spots in this room got flutter? one spot, maybe around where
Jack is.
around where Jack is, right? Yeah, see? So is it fluttering between there, or side by side? This way, right? Because the glass and there, you see, between two parallel hard surfaces. So every room also will have some kind of flutter one, lah, right? If not, it's not perfect, lah. So very easy. Next time, again, experiments. Go around, clap your hands. Okay, Jack, maybe you try clapping there. Can we hear? Can you hear there's a bit of a slap back? So that's flutter echo. Here don't have. Here don't have, okay? I don't know. Maybe everyone try a clap. Colin, clap. Got a bit. Because again, from the ceiling and maybe that wall over there, see? So but over here, don't have. None. Or minimal. Very, very minimal. Okay? So that happens between, right, parallel hard surfaces. So go back home, clap, right? Maybe your friends and family member thinking, what happened? You crazy already. They say, oh, I'm trying to listen for flutter echoes, okay? So flutter echoes, right, are like that. They're caused by repetitive reflections of the hard surfaces. So the black boxes, those are your speakers. So if you have flutter echoes, the problems with flutter echo, imagine what it causes havoc. The sound is like bouncing very, very quickly back and forth, side by side, front to back. It can also cause these issues. So now, how do you do with flutter echo? Okay, it's very easy to deal with, right? You just apply mid or high absorbers, for example, foam, right, across one of these walls. I'm quite sure the back there where the drums are, there's probably no flutter here, okay? Because it'll be bad to have flutter echo where the drums are, right? Because especially with drums, because they're loud. So that's why you see, that's exactly why, the studio here has positioned all the foam panels a certain way. Not because of decoration. There's a purpose behind it. Okay, now moving on. Comb filtering. What is that? It's related as well. They're all kind of related in one way or another. But comb filtering, it occurs due to interference that exists between a direct sound and reflected sound from the same source. So let's say you have a direct sound coming from one here, then another one bounces off the wall and then arrives at your ears. So when the two bounce and they reflect back, so when you have two different waves, you get some interference and you can get something called comb filtering. So the reflections will cause a bit of time delays. A resulting waveform, right, will have notches and peaks. It looks like this. So you will get this in certain areas of every room. So comb filtering is very bad, okay? It's bad because what happens is that it will make the sound very thin because it's like all those frequencies, right, get cut off. You get all these kind of dips inside the frequency. So generally, if you hear comb filtering, that's very bad, right? You hear something that sounds very comb filtered, it sounds very thin, it sounds very hollow, and it sounds like it's got a hole in the whole sound because of all those frequencies that are missing. Okay, let's move on. So after comb filtering, okay, let's talk about early reflections and your stereo imaging. Early reflections, right, occur when the sound from one speaker bounces off the sidewall. Okay, for example here, you bounce off the sidewall and then a few milliseconds, a microsecond after that, it enters the ear. So is that good or bad? That's bad, right? Because what happens is that the sound, instead of traveling straight from your speaker to your ears that you hear it accurately, it is now bouncing around the wall and giving you those issues. It will result in some comb filtering. It also results in a smearing of the stereo image, and that's also very, very, very important as well. So instead of hearing the sound coming directly from the speaker left, right, on the left-hand side, because you're hearing the sound source also coming from the wall, right, that is reflected from the wall. Not only is it delayed, but it's also at a different area. Your stereo image is not solid already. You hear it's smeared out. So instead of hearing it there, you hear it like Similarly, I did mention, I explained, right, how some sampling, like to me, sampling rates give a much better stereo image. This is also another factor as well to stereo imaging. So many problems, right? So many problems. How to do like that? We all cannot do anything. So in these instances, the left ear believes that it hears the sounds in the right. What can happen is that the sound in the left speaker can come from the right speaker. Because let's say the speaker on the right, it's bouncing off here and then traveling into the left. It's possible. So what happens, your stereo imaging gets all messed up. Okay, now moving on. What are the room ratios? Okay, scientists and acousticians have already done some research. They have identified, right, that there are some ratios of the room, right, the nisbah, in order to minimize the acoustic problems. So these are the series of ratios that they have determined, right? So this is always height, width, and length. So let's take the height of 1.1, then the width 1.14, 1.39. Now, so this table, all right, you can actually take back lah. All right, later on I'll send you the, right, you can always refer to it. So if you were to design and build a room, right, in order to give you minimal acoustic problems, this would need to be the ratio. So if your height, let's say your height is, I'll use feet because it's easier lah, right, more logical. If you're 10 feet in height, then your width needs to be, right, 11.4 feet, and then your length behind needs to be 13.9 feet. So that will give you the ideal room ratio. The worst room ratios are, of course, right, the cube. If it's 111, that will give you the most problems, maximum problems. So when you design a room, you have to, or if you have a room at home, look for one lah, which is as close as possible to these ratios. Okay. Now let's move on. Okay, so how do you get your home studio sounding right? How? Let's take this case study, okay? Right, look at this home studio. Wow, it's quite messy. Okay, so let's look at some of the problems. Number one, asymmetrical positioning. So asymmetry, okay, means that the positioning of your speakers, especially, right, and all equipment is not symmetrical. It's off to one side. That will automatically, it will give you some problems with the reflections. Number two, speakers too close to the wall, right? When it's too close to the wall, you get, first of all, right, couple of issues with the bass buildup. Number three, speakers not angled properly. You see this speaker over here, the one on the left is like 90 degrees off. Then the one is like, saying it like that a bit. You're not angled properly, right? You're not angled properly, you're not hearing an accurate stereo image. Then number four, speakers not on the stands, not at head height, okay? A lot of people are guilty of this lah. They just put on a table or something like that, okay? Understandably, sometimes space constraints, sometimes budget constraints, but what you want to do is you want to put it, at least make sure that it's the same, your tweeters, right, are the same height as your ears. So correct speaker placement, how do you solve that? You should always avoid being too close to the corners and the walls. And too close here meaning, right, 0.5 meters. So 50 cm. At least lah, that's recommended, right? The further away, it's even better. But of course, see what's the size of the room lah, it's practical, okay? Now, you want to position your monitors, usually, generally speaking, along the short wall. And this is what I mean. Generally, this is better. You position it this way along the short wall and not the other way around. And the reason again being because you look at the reflections. If it's on the short wall, right, the reflections that go back that way, for example, by the time they bounce back, the energy, they have lost a lot of energy and they're a lot softer already. So not so much issues. But if you position it this way, the other way around, you have your speakers there. When it fires back, the reflections are much nearer, much stronger. See? So you want to check for correct speaker orientation as well, okay? Whether the speaker is vertical or horizontal. Some speakers, right? Like for example, the ones that are in here, they are designed to be horizontally placed, mounted. Some speakers are meant to be vertical, all right? So that will affect your sweet spot as well. So speakers and listening position should form an equilateral triangle. So what's an equilateral triangle? Equilateral here means that, right, the angles between all three sides are the same. 60 degrees, 60 degrees, 60 degrees, okay? So your high frequency drivers, that means your tweeters, right? Not tweeter, tweeters, right? The high frequency tweeters should be at least same height as your ears. Your listening position should be centered. For example, in this graph, center of the short wall, right? The speakers are also centered. The tweeters, right, are the same as the height of the head, especially the ears. Use stands and avoid placing on desktop or other resonating surfaces, okay? Now, because if you put your speakers on the stands, even though if it's at the right height, the thing is that they are not solid enough, right? So if you have, let's say, a wood table or even a steel metal table, when the speaker resonates, when it vibrates, it will cause the table to also vibrate. So it will vibrate at a certain frequency, then you hear that frequency, it affects your accuracy. So now if you're not able to use a stand, right? Stands are always the best, recommended, right? There are always isolation products. So for example, these are like the Acoustics stands, and these are foam isolation pads. Now, obviously the isoacoustics ones, those are much better, right, performing than those. I think there's also some over there inside those speakers are also resting on those. Foam isolation pads are better than nothing, but they are not so great, not so helpful. I personally have tried it myself, right? I added it, I compared, I even added it on top of stands. Not much difference. Doesn't really help that much. It's better than nothing, but at least it helps a bit lah. Most speakers nowadays, walls or monitor speakers, have some kind of speaker adjustment settings. So you want to tune them according to your room. So for example, they will usually give you some diagrams and reference or in the manual they will usually state it. Depending on how far it is from the wall, depending on where it's located, depending on whether you are putting on a table or you're putting on stands. Sometimes they have tuning, right? You can always tune, right, at the back. Okay, most monitor speakers will have some kind of a speaker calibration or speaker tuning adjustments. To get your home studio sounding right, you want to apply some basic acoustic treatments. Use products such as acoustic foam or broadband absorber panels. Okay. So, for example, most of these are acoustic foam. Maybe the long ones are absorber panels. Okay, check out brands such as Auralex, Prim Acoustic, or you can always DIY. Okay, all these things can be very simply DIYed. So, acoustic foam, diffusers, or this is like, for example, this is a whole kit from Prim Acoustic. I think for a small room, right, they sell the kit called the London 8 kit. Right, I'm not promoting, right, just saying on it. Okay, which is actually about 1,008. It's not that expensive, and for very good quality product, right? You can actually get those locally. Now, you want to use bass traps in room corners if you can get. So the middle one is a bass trap. So as bass frequencies will build up where the wall meets the ceiling. If you can afford, you can use bass traps in the corners. So where would you want to apply all this? Now, the goal of acoustic treatment is you want to create what we call a reflection-free zone. Right, so where you are sitting in front of your speakers, in front of your computer screen and monitors, right, you want it to be a reflection-free zone. You place acoustic absorbers at the first reflection points. They call it mirror points because it's a very easy way to find out where these points are. You take a mirror, you get someone, a friend or family member to help you, and then you sit at your speaker position at your monitors. You get the person to hold the mirror on the side of the wall and just walk. Anywhere you can see the speaker in the mirror, right, that's a reflection point. So you want to put your acoustic foam over there. This one you need a friend to help you or family member. Just hold the mirror. You can see it, that's a reflection point. So you walk along the side, if you can see the speaker, that will be reflection point. Here it also mentions, right, ceiling absorber at the mirror point. Now, if you can install, right, you can also put a ceiling absorber. As you can see above there, we also got some absorbers up there because don't forget, we also have ceiling also, okay? Right? Obviously, you cannot put on the floor unless you want to be stepping on the thing, right? Side absorbers at the mirror points. So rear walls can be treated with a combination of either absorbers or diffusers. So in a small room like this, right, mostly we want to use absorbers. So what are diffusers? Okay, let's take a look. You've seen these? So these are different types of diffusers. So what diffusers will help to do is they help to scatter the sound randomly. Now, if you use absorbing materials, panels or foam, sometimes what it does, it will cause the room to sound too dead, right? So diffusers are good in the sense that they will still maintain the natural liveliness of the room, but because the sound waves is being scattered, they don't cause the same problem as what they do if they have a hard reflection. Once it's scattered, it's okay. It's fine. It's a lot better. It doesn't cause you so much of a problem. So diffusers are also another way. If you feel that the room liveliness is there, because if you make a room too dead, it's not natural, right? We feel very, if you go into like a soundproof room, right? You stay there for too long, right? You start hearing things, you start going crazy because you cannot hear. It's not a natural sound. we naturally need to hear a little bit of room ambience one. Then you feel very comfortable. Okay, now moving on. You also have what we call panel-based traps, okay? And Helmholtz resonators. Again, won't go too much into detail. These are much more specific. These can be tuned to specific frequencies. So if your room, right, has a problem at 100 hertz, these can be built and constructed and tuned to tackle those frequencies. So for example, these are panel-based traps, right, and Helmholtz resonators. They are built into the wall already, okay? Of course, this is a lot more expensive and need a contractor to do it, right? Okay, now, as I mentioned, what are the common myths and misconceptions? Acoustic treatment, number one. If you remember the first thing, this is the one. Acoustic treatment is not soundproofing, okay? So be careful of companies that sell soundproofing products, okay? Especially when there's no data involved. You see a lot of that, unfortunately, okay? And the funny thing is that we won't buy products that not Sirim approved by Sirim or something like that again, right? All your electrical products, right, must have Sirim approval before it can be sold, because we know with the Sirim approval it works and it's safe. These are the two things. So why would you buy acoustic products which has no data or anything? You don't know whether it works. You just buy it, okay? Now, egg cartons and other great acoustic treatments, for example, carpet lah, packing foam lah, mattress, okay? These are not great acoustic products. They offer little to no absorption in the lower frequencies, right? It affects does not help with the low frequencies at all. Now, carpets, right, first of all, are not recommended to install on walls or ceilings. They're not designed. You go to a carpet product, they always tell you, and there always be a disclaimer cell, not intended for use on other surfaces besides floors. It's meant for floors only. Another major issue that a lot of people forget: these are potential fire hazards. Proper acoustic treatment or acoustic products, like for example, I think these are all mostly Auralex panels. They are already fire treated, or they are, made with material that has fire rating. Now, I won't go into details, but you go onto YouTube, right? You go and look at some of the videos, right? Especially the fire, the bomba demonstrations. They will show you how fast a common household material, like a curtain or a bed or mattress, will catch fire just from a single spark. Very fast. It's very scary, I tell you, right? So you don't want to be putting these kind of products, right? Egg cartons lah, and all the non-fire treated foam inside your house, inside your home, your family. Something goes wrong, a fire or a spark or cigarette butt or short circuit or anything, the room will go up in flames in seconds, right? Less than 1 minute, you have a big fire already happening. We'll cover one last topic, and then after we take this short, quick break, okay?